The Ls-Dyna Implicit training includes 9 lectures and workshops. Now let's start the lecture 1, Implicit versus Explicit. What are the differences between implicit and explicit? The implicit and explicit are defined by their time integration algorithms. In explicit time integration algorithm, internal and external forces are summed at each node point, and a nodal acceleration is computed by dividing nodal mass. The solution is advanced by integrating this acceleration in time. The maximum time step size is limited by the Courant condition, producing an algorithm which typically requires many relatively inexpensive time steps. While in implicit time integration algorithm, a global stiffness matrix is computed, inverted, and applied to the nodal out-of-balance force to obtain a displacement increment. The advantage of this approach is that time step size may be selected by the user. The disadvantage is the large numerical effort required to form, store, and factorize the stiffness matrix. Implicit simulations therefore typically involve a relatively small number of expensive time steps. The time integration is in the integration of the equations of equilibrium governing the linear dynamic response of a system of finite elements. For static analysis, the velocity and acceleration-dependent forces in the analysis are neglected. The choice for a static or dynamic analysis is usually decided by engineering judgment, the objective thereby being to reduce the analysis effort required. However, it should be realized that the assumptions of a static analysis should be justified, since otherwise the analysis results are meaningless. Indeed, in nonlinear analysis the assumption of neglecting inertia and damping forces may be so severe that a solution may be difficult or impossible to obtain. The explicit and implicit direct time integration can be written in a conceptual forms. For explicit analysis, the equation shows that the solution depends on nodal displacements, velocities, and accelerations at state n. All quantities are known. Therefore the equation can be solved directly, explicitly. For implicit analysis, the equation shows that the solution depends on nodal velocities and accelerations at state n+1, quantities which are unknown. This implies that an iterative procedure is needed to compute the equilibrium at time t to n+1. In implicit analysis, convergence is a big concern for a complex nonlinear models. In Ls-Dyna there are 3 such criteria, where the setting can be controlled by the user. The 3 different criteria are energy, displacement, and residual. Only the first 2 are activated by default. All activated criteria have to be satisfied in order to achieve convergence. The first convergence criteria is energy convergence. The energy check compares the current energy norm to that of the beginning of the step. The value of ectal is default set to 0.01 and can be changed in *control_implicit_solution card using ectal. It is seen that if the external load does not change from the previous step, the residual, R1 will be initially 0. This will cause problems for the energy criteria since the denominator approaches 0. In this case Ls-Dyna displays an energy norm of 1.000. It is recommended to apply a load that varies in each step. The second convergence criteria is residual convergence. The residual criterion compares the residual norm ratio against a user-defined tolerance. The criterion is not flagged by default but can be activated by the recoded option in *control_implicit_solution card. The third convergence criteria is displacement convergence. The displacement criterion compares the displacement ratio against a tolerance, dtol. The default value of dtol is 0.001 and can be changed in *control_implicit_solution card. In Ls-Dyna, there are 2 options to calculate the denominator in the displacement tolerance criteria. This is specified by the dnorm flag. dnorm equals 2 is the default, which uses total displacement and becomes less strict as total deformation increases. dnorm equals 1 uses displacement in current step, and can often use larger dtol. There are advantages and disadvantages for each of the methods. Implicit is unconditionally stable and applicable for static models. It is relatively inexpensive for long time duration but requires much larger amount of memory dir to the store and update of large stiffness matrix. The biggest issue is that implicit often have convergence problems with complex nonlinear models. Explicit analysis is computational fast, robust, even for very complex nonlinear problems. But explicit analysis is conditionally stable and expensive to conduct long time duration. I will show this later using a simple model. Implicit and explicit are used for different applications. Implicit is usually used for low-rate dynamic analyses, static simulations, eigenvalue analysis, springback, gravity loading, preload etc. Explicit is usually used for high-rate dynamic analyses, vehicle crashworthiness and airplane airworthiness analyses, impact/penetration problems, explosives, quasi-static analyses etc. Due to the differences in the two methods, some keywords need to be recoded in order to work with implicit. These are the ones that the user should be sure are working for the implicit solver before using them. Some of these are material cards, contact cards, boundary cards, constrained cards, and element types. We will discuss these cards in later lectures. Ls-Dyna's implicit mode may be activated in two ways. One is using *control_implicit keywords. A simulation may be flagged to run completely in implicit mode. Alternatively, an explicit simulation may be seamlessly switched into implicit mode at a specific time using the *interface_springback_seamless feature or using a load curve. The seamless switching feature is intended to simplify metal forming springback calculations, where the forming phase can be run in explicit mode, followed immediately by an implicit static springback simulation. In case of difficulty, full restart capability is supported. This is a workshop. The purpose of the workshop is to show the differences between implicit and explicit. The point force load is applied at the beam tip. The material is linear elastic steel. The dimension and material properties are shown in the slide. From the theoretical calculation, we can get that the deflection is 3.70 mm. You need to create the model and solve the cantilever beam deflections using both explicit and implicit analysis methods. This is the comparison of the control cards used in explicit and implicit methods. The time step card will be ignored when implicit analysis is activated. In implicit analysis, control_implicit_auto and control_implicit_general cards are added. The purpose of control_implicit_auto card is to define parameters for automatic time step control during implicit analysis. IOTO equals 1, analysis will automatically adjust time step size. More options will be discussed in later training lectures. Purpose of control_implicit_general card is to activate implicit analysis and define associated control parameters. This keyword is required for all implicit analyses. InFlag equals 1 activates implicit analysis. More options will be discussed in later training lectures. This is the comparison of the beam deflections obtained using different analysis methods. The deflection obtained using explicit is much larger than the theoretic solution, while the value obtained using implicit method is very close to the theoretic solution. If we check the deflection history, it could be found that the beam deflection solved by explicit is not stable, it is in vibration mode. The beam deflection solved by implicit is very stable. Since this is a typical static problem, implicit analysis is right method not only because it is stable and accurate, but because it is much faster than explicit. If using explicit analysis method, the time duration must be large enough to reduce the oscillation. This is the deflection result using much slower loading rate. As can be seen, the oscillation of the beam tip is significantly reduced. Next lecture topic, Lecture 2, How to Activate Implicit Solver. If you are interested, please don't hesitate to subscribe the CAE Training and Consulting channel. More CAE training lectures will be coming soon. Thank you for watching.